going on, everybody? It's Mr. Gus, and I'm back in the physics classroom. And here, we're back starting our new unit. So in order to start our new unit, what I thought we would do is we would look closely at some former material. So I'm going to give you a challenge problem, and we'll solve it together, and then we'll go ahead and add something to it just to see what that might do and what other topics we might need to study. So we are going to take this green car here with a mass of, let's call it M, drop it down this ramp, and as it reaches the bottom of the ramp, it's going to leave the ramp, and we're going to predict where it hits the ground. We've done this kind of problem before, but we're starting a new unit, so let's try it again. First, let's start with our picture. We have a picture, the ramp, here it is. It ejects off the table. It leaves with initial velocity. We can call it Vx. Over there, we know it starts up here at the top of the ramp with an initial velocity equal to 0 meters per second. It is at a height, we can call it delta H up here, and the table has a height of delta Y. Our job is to predict the range where the car will eventually hit the ground over here. Okay, so if we think back about this, I see a curved ramp. It might be really hard to see, actually. Maybe I should go over this in black marker because of the glare. It's sunny outside and we love it. That's a terrible marker. Get rid of it. There it is, there's our ramp. Now, what's weird about this ramp is that it is curved, right? It's flat here, but then it curves. So using forces over a curved area is gonna be a really tough task. There's gonna be a changing component of gravity pulling it down the ramp, and then therefore any kind of friction, which is relatively negligible with wheels, is gonna also go away. So we don't really wanna rely on kinematics and forces over here. So instead, let's rely on energy. An energy problem where my system includes the car and the earth, so I can use UG as a part of my system. So if I think about this point over here as point A, and this point over here as point B, and I think about my system being the car and the earth, well, I can go ahead and write myself a conservation of energy expression, or an energy expression, where my initial energy plus any outside forces known as work will be final energy. Initially, there is energy stored between the positions of the car and the surface of the earth, or in this case, the table, the lowest point in that system. There are no outside forces other than gravity pulling it down, so there's no work done. And at point B, I'm going to see a kinetic energy at point B. This ends up being my energy equation. So I can go ahead and solve for my speed, Vx. This is my delta H equals 1/2 mv squared. My masses drop out. I'm left with G times delta H equals 1/2 v squared. And what I end up with was V at x is going to be equal to the square root of 2G delta H. Let's think about some data here that I might need to take. I'm going to need to know how high above the surface this car starts. So my delta H is equal to 0.41 meters. That's a variable I need to know. And once I know that, I can go ahead and solve down here for that. So the square root of 2 times 9.8 times 0.41 meters is going to be my speed. And I end up with a velocity being equal to 2.8 meters per second. This is my velocity as it leaves the ramp. So I've kind of figured this out. The second part of this problem is figuring out, well, where's it going to land? How far? What is the range? It's my kinematics or my bomber problem. So for us to do this, I need to think about all of my x variables and all of my y variables. I need to think about my change in x or my change in y positions. I want to think about my initial velocities in the y direction, maybe my final velocities in the either direction, and certainly think about time and acceleration. Now, we have to remember that time in both directions is equal. These motions happen simultaneously but independently, so time is still going to be equal. If I think about delta x, well, that's what I'm solving for. Delta y, I don't know, but delta y is the height of the table. It's the height it falls. So let's take a measurement. The measurement from the ground up is 91 centimeters, or 0.91 meters. The initial velocity when the object is launched horizontally in the y direction is 0. My initial and final velocity in the x direction, well, that's Vx. That's what we solved for over here. Final velocity, I don't know what that is. That's a blank. I'm not sure what that is. Time, I don't know, but I do know that those are equal to each other, so I'm going to have to eventually use time to figure out what's going on in the x direction. A is equal to g in the y direction, which is 9.8 meters per second squared downward, and in the x direction, it's 0 meters per second squared. I think I can solve this. I think I've got a way to solve for time. If I think about the y direction, I know that change in y is equal to the initial velocity in the y direction plus t, or times t, plus 1/2 gt squared. The initial velocity is 0, so now all I need is 0.91 meters is equal to 1/2 times 9.8 meters per second squared times the time it takes to hit the ground. I can go ahead and solve for this, right? 2 times 0.91 divided by, over here, 9.8 is going to be equal to the time. And I end up with, I think, something close to 0.4. 2 times 0.91 equals this, divided by 9.8 gives me something like, and then the square root, sorry. And also square root the answer. Square root of that answer. I end up with 0.43 as my time. 0.43 seconds is the time to the ground. And then to find finally the x direction, I take my speed in the x direction, multiply by how long it's going to be in the air, and that will be my time. So let's take our Vx from over here, which is 2.8. Let's multiply it by the time we just solved for, which is 0.43. And we end up with a change in x. Let's see if you can see over here. Our delta x is equal to 1.2. I get 1.2 meters. And so if I think about where on the floor that is, that's somewhere over here. I'm going to mark it on the floor. 1.2 meters. It's on the floor. I've marked it here. Okay, you see some of my classes marked it. Over here is 1.2. This is our second mark. So here's 1.2. So when I drop this thing down the track, it should land here. Let's check it out. 3, 2, 1. Does it land there? Ooh, it's really close. It ends up getting really, really close to that mark. Fantastic. Our conservation of energy is within error. It happens within error, meaning there might be some friction on the ramp, and if there is, fine. It is still close enough where 1.2 makes sense. Here is where, that's all review. Here's a new scenario. A new scenario is going to be, what if instead, instantaneously at the bottom of the ramp, the mass doubles? At the bottom of the ramp, I put a second car. And that second car sits right here. So this green car comes down the ramp, collides, sticks, creates a new doubly massed object at the very bottom of the ramp, and then leaves the ramp. So instantaneously at the bottom of the ramp, I go from 1 car to 2 cars. The mass automatically doubles. So let's think about this. If this is the case, the change is going to happen over here. The change from UG to K, UG is mgh, but K is 1/2 times double m, 2m v squared. This is the change over here. This is what happens. Let's go ahead now. If you want to, pause this video. You solve for where it's going to land now based on our new change in mass. All we're changing is the initial speed it leaves with. Okay, if I double the mass, what's going to happen to the speed? So go ahead and calculate that. I'm going to do it here. You can pause it or not. Up to you. I'm going to solve it here, though, right now. I end up with is 2.0 meters per second, which makes sense. It should be less. It was 2.8, and now it is 2.0. So there's a decrease in the amount of speed that it has. Perfect. Now I go ahead and I don't change anything about the y direction. All I'm changing is the x direction, or the x distance. And so when I go ahead and do this, it's 2 times 0.43 is 0.86. So my new displacement in the x direction, according to conservation of energy, is 0.86 meters. And that's what you see on the ground over here. What I have on the ground over here is some students have already marked, you can see right here, This is where 0.86 is, and that red mark you see on the ground is kind of my error line. Like if it reaches over that line, we're probably going to be in a good spot where these two, or where any kind of sources of error or real-life frictions might cause this thing to slow down and give us a smaller number than we would expect. So that line there, if it gets over that line or touches that line, we know we're in good shape in terms of within error. I'm trying to get this tape to roll so I can get these things to stick. So I'm going to go ahead and put tape at the front of this car and tape here on the back of this car. And I'm going to go ahead and drop this thing. 3, 2, 1. Let's see where they land. Ooh, so we ended up landing here. They stick, they land after they hit the ground. Obviously, they break apart. But we land way down here. And that's an issue. Okay? There's an issue. The issue is that understanding from first semester where conservation energy is conserved initially, I'm confused, right? There's a collision that happens here. We double mass immediately, and something else happens. Well, if I think about this, what ends up happening is I hear a collision. I hear a collision taking place. Collisions, when a collision happens, we hear a collision. There's bending of metal sometimes or objects, but almost always there is sound. And sound energy is not considered a mechanical energy. So, technically speaking, my conservation of energy expression is not valid in a collision. In this case, this conservation of energy expression is not valid. So off the bat, there is an issue with me solving this problem because clearly I land way short. We're missing something. And apparently the collision produces a lot of sound energy given how short we were away from our goal. So this is what we need to study, and we'll study this over the next few weeks. We're going to study the idea of momentum. When things collide, it's not that energy is necessarily conserved, but momentum is. And momentum is sometimes called moving inertia. I wonder why. I want you to brainstorm, think about reasons why momentum might be moving inertia. Think about ways and times you've heard the word momentum before, and what characteristics you think might have momentum. Do you think a bowling ball will have more momentum or a tennis ball when I drop it off the table? I wonder why. I wonder what are some factors that play a role in momentum. Once you've thought through those, I would like you to go into the packet and go ahead and complete the introduction to momentum and think about things from first semester, how they might relate to second semester, and what momentum might be. Okay? If you have questions, as always, drop it in the comments, send me an email, ask me in class. Until next time, see ya!